A equal to opt. What is A? A is our algorithm, the number of intervals accepted by our algorithm. A is that number. So cardinality of A is that number. Okay, if you remember it. And opt is basically some oracle or some imaginary optimal algorithm which gives the optimal solution. And this cardinality of opt is the number of intervals accepted by the optimal algorithm. So we cannot say exactly what are the content of A. That means what are the exact intervals that A has accepted, what are the exact intervals that opt has accepted, but we just want to show that their numbers are same. So what we assume, I think I told that we assume that, okay, let's say this opt, we assume that let the intervals are added in like J1, J2 up to Jm. Okay, something like that. And this opt, this A, let the intervals be added as I1, I2, etc., ik. A not equal to M for the time being, we assume. Okay. Because if we assume K equal to M, then it's done. There's nothing to prove. Okay. We are actually in the process to show that K equal to M. Okay. So now let us assume that they are not same, that is K not equal to M. So how do we do that? So first we want to show that we ask ourselves, okay, this question: that can the greedy algorithms rth interval, let's say any rth interval, finish later than the same in the optimal algorithm? Okay, probably there is some doubt in that. Okay, so for example, I claim this fact that f of I1 is less or equal to f of J1. Why I claim this? Because see, our algorithm has chosen I1 as the first interval. Why did it choose the first one? Because it went through the heuristic that choose the smallest finish time first. So if this were not the case, that means if it were the case that if I1, sorry, if I1 was greater than fj1, then our algorithm, instead of choosing I1, would have chosen J1. Correct. So that's why we say that this cannot happen. Okay, this cannot happen. Okay, so this is the claim that if I1 is always less or equal to fj1, that means the finish time of I must be smaller than or equal to J1. Okay. Now this thing we want to show in general. In general means at least for we assume that K is less than M. Assume that K is less than M. Why we assume K is less than M? Because we feel that our algorithm is suboptimal and optimal is the best, basically. So we want to actually, the statement of the lemma that we are going to prove is something like, for all r less or equal to K, if IR is less or equal to FJK. if JR. That means up to K, for all the intervals, the finish time of the accepted interval, according to our algorithm, is always smaller or equal to the finish time of the corresponding interval that is in this sequence J1, J2, Jn. Okay, so this thing we prove by induction. Okay, prove by induction basically. Okay, so how this is actually proof for case I equal to 1. Okay, I equal to 1, this is the proof. And this is nothing the proof, it's the basically base case I equal to 1. That first interval of the accepted by algorithm A is actually smaller or equal to, I mean, if I1 is less or equal to, I think this is the argument is clear to everyone. Now, the second step of induction is naturally the inductive step, which says that let us assume, what is the assume? Up to R. I R minus 1. Finish time of R minus 1th interval, according to our algorithm, that is less or equal to finish time of J R minus 1. Okay, this is the inductive state. I assume that this is the case. And what I intend to prove with these two assumptions, we want to show that if IR is less or equal to FJR. If we can somehow show, then probably we are done, right? Then I can say for all up to K, this is true. Then we will argue about, I mean, this, I mean, what happens to the rest of the cases. Okay. So up to this is okay. Inductive step, I think is okay. Now, one thing, how to prove this? How to prove this? So we do like this. I can write that f of J R minus 1, that is the finish time of R minus 1th interval as accepted by the optimal, that must be the smaller or equal to the start time of JR. That means I'm now looking at the optimal algorithm and just looking at the two intervals that are inserted one after another. One is JR minus 1, another is JR. Okay. Now, definitely, I mean, if they are not compatible, then they cannot be in the optimal, because if they are not compatible, they cannot be served because they are overlapping, right? There is a single resource, so they cannot be served. So it must happen that R minus 1 and R must be compatible. So in that case, I must write that R minus 1 must finish before the start of the next one, that is JR, right? And if you just now look at the inductive assumption that if f of I R minus 1, that is the finish time of the R minus 1th interval, according to our algorithm, that is smaller than the finish time of the finish time of the R minus 1th interval in the optimal algorithm. So if I club this, if I join these two inequalities, then obviously I can write, I mean, this thing and this thing, this together, they give f of I R minus 1, this is less or equal to S of JR. Okay. You agree with this? Right. So what does this mean? This means that the finish time of r minus 1th interval, according to our algorithm, is actually less or equal to the start time of the rth interval in the optimal algorithm. That essentially means that if you just consider the r minus 1th interval according to our algorithm and the rth interval according to the optimal algorithm, they are actually compatible. They are also compatible. They are also compatible. But incidentally, our algorithm did not choose JR. Instead, it chose IR. Instead of JR, it somehow chose IR. It somehow chose IR. Right? That is something. So they are still compatible. This R minus 1 and JR, they are compatible. And IR minus 1, this R minus 1 is compatible with R, of course. But somehow, instead of our algorithm choosing this JR, it chose IR. Okay. So why it chose IR? I asked myself this question. Why instead of choosing, because JR is compatible, IR is also compatible with this RI minus 1. I mean, R minus 1 at interval. So why did it choose IR instead of JR? It is mainly because of the condition of choice that I choose the interval which has earliest finish time. So had it been the case that the finish time of this would have been greater than the finish time of R, JR, then because JR is compatible with R minus 1, our algorithm would have chosen JR. But that has not happened. Why? Then it must be the case that finish time of IR is less or equal to the finish time of JR. It must be the case. That's why it chose IR. Okay. And this is the thing that we intended to show. Right. This is the thing we intended to show. Right. So up to K, this is okay. Right. Now, I think the proof is now clear. Next is just induction. I mean, I do it for 1, I do it for 2, I inductive, right? So I can show that this is true up to all, right? So now, I mean, the tricky thing comes into that how to show that K equal to M. Okay. Again, we assume that K less than M. Again, we assume that K is not equal to M. K is less than M. Okay, then what happens? If K is less than M, then we have already shown that up to K, this is the case. I mean, up to K, what happens? F of IR is less or equal to F of JR. Okay, R less than equal to K. Okay. Then after this, what happens? After this, why our algorithm failed to find something more? That means after this step, after k intervals, after finding this k, there is no other interval left in the set. That's why our algorithm stopped. Because if you look at the stoppage of our algorithm, it says until the set R is empty. Say R is the set of all intervals probably. But somehow the optimal algorithm has not stopped till that time. And it has still intervals of this form like J, K plus 1, jk plus 2 up to jm, because it stops after m, right? So now we can claim like that if I of k is less or equal to fj of k, I can write like that. This is from the earlier lemma. The finish time of the kth interval, according to our algorithm, is actually smaller than the finish time of the kth interval in the J's algorithm. I mean, in the optimal algorithm. Right. And again, I can, if I look at the optimal algorithm, I can write that f of jk is less or equal to f of jk plus 1. That means, sorry, this has to be, this is not f, this is s. That means the finish time of, and now if you look at the optimal algorithm only, the jk, that means the kth interval, must be compatible with the k plus 1th interval. That the finish time of k in the optimal case must be smaller than the start time of the k plus 1. Okay. So again, if you combine these two, then what happens? You can write f of ik is less or equal to s of jk plus 1. Something like that. What does this mean? That means that the interval that is the kth interval in our case, that is actually compatible with the k plus 1th interval as accepted by the optimal algorithm. So they're compatible. So what is the argument? The argument means that after accepting k requests, okay, in the optimal algorithm, still has more elements, more intervals to accept, like jk plus 1, jk plus, I mean, not jk plus, k plus 1 is interval to accept, then k plus 2, in this way up to m intervals. Whereas the greedy algorithm has stopped because R has become empty. But it is something contradictory, because if optimal algorithm still has those compatible things to take, then our greedy algorithm could have taken this k plus 1, right? That means this k plus 1 must have been taken care of either earlier or it is not at all there. Okay. So this is some sort of contradiction. Okay. So that means it cannot happen that the greedy algorithm has stopped and it has found the R to be empty, but the optimal algorithm has yet not done, and it still has many intervals to accept. And also those intervals are compatible to be included in the greedy algorithm, as per the greedy algorithm. So if the greedy algorithm finds that these intervals are still there, k plus 1, k plus 2, not included in its list, then they would have been taken because they are compatible. But our algorithm, greedy algorithm, has stopped because there is no further interval. But the optimal is finding it. So that means this is a contradiction. So this thing that k less than equal to m, this cannot happen. This cannot happen. So we must say k is exactly equal to m. Okay. So this is how we show that that the the cardinality of opt is equal to the cardinality of A. Okay, so this completes the proof. Now, so if any questions till this point. Okay, so what is the running time of the algorithm? What is the running time? It can be uh, it can be shown that the running time of the algorithm is uh, of the order of time taken by the algorithm is n log n. How? We the first step we do is we sort the n requests based on the finish time, increasing finish time first. I mean, in the increasing order of the finish time. Okay, that sorting requires this much of time. And then we do uh, uh, what we do, we actually take the first interval, okay? We take the first interval in this sorted list and we remove all the other intervals that are conflicting with this one, right? So actually each iteration, we actually iterate from say left to right, say I minus, I mean index, this I here is index. Let's say I designate it by I. So I equal to 2 to, let's say n, okay? You check whether this is conflicting. For each case, checking whether it is conflicting, I just need to check whether the finish time, whether they are overlapping or not. Overlapping and non-compatible, there is this checking function like finish time of, let's say this interval, the first one is, I can say I1 is less or equal to the start time of, let's say this is J, okay? I J, or I can say that the finish time of Ij is less or equal to start time of I1. So for all J, I do this basically. So what this means? This essentially, this is the overall condition. If I check, then I can basically uh, check whether they're compatible. If they're compatible, then I keep it for the next consideration. If they're non-compatible, I just discard that J. I just discard that in, okay? So in this way, I do it. How long I do it? I do this iteration number, okay? And I take the next interval. I again, in that case, probably some intervals will be deleted in the first round. So probably my list becomes smaller. Okay, so in subsequent time, probably I need not go through this thing. I probably need not go through this entire thing. Okay, that means when I1 has been taken, when I2 has been taken, then in case of I3, might be that I do not need to move through all of them. Okay, and there, so maybe I can use better approaches of implementation so that I do not need to go through all of them. Okay, so probably I can do better. And this see each interval when I do this kind of checking, etc. I spend actually order one time, and overall it can be shown that this entire processing, okay, for all of them, this doesn't actually cross more. Okay, so overall time actually can be shown to be dominated by this sorting time. Okay, so overall time is n log n.
Sir, hello, sir.
Yes.
Yes, sir. Is the screen sharing turned off?
Oh, how so? Let me see. Oh, okay. What happened? What happened? Just a minute. I even somebody. Yeah. Now is okay.
Yes, sir.
This. I hope I did not miss much.
So actually, that algorithm discussion for that time it was not visual.
Okay. Okay. I
Yes.
think it's okay. So. Uh, so does anybody have any questions till this point of time? Just 1 minute. Just 1 minute. Hmm. Uh, okay. Does anybody have any questions? There is something. Where is that leaf? There is. Mm, just a minute. Yeah. So anybody has any questions? Okay. So this is, I think, is up to this point is okay. So so this clearly shows that we have designed one algorithm which can optimally solve the problem. But remember one thing again and again, I am saying that it may be the case that the number of intervals accepted by our algorithm is equal to the number of intervals accepted by some optimal solution, but the set may or may not be same. Oh, actually, there is something wrong. Mm, the screen sharing is being stopped somehow. I do not know whether this is due to recording or not. Somebody is recording things.
We can stop that.
Mm, okay, let it go. I think it has let's see for some time. Okay, so there is another. There are various other versions of the problem, and I will request the students to go into the chapter 4 of the Kleinberg Tardus book. Okay, so there are many problems to deal with. For example, the first, let me just name the problem. I mean, the first thing is interval scheduling problem. Okay, now it has different variations. I mean, it has different variations. One is a simple problem. Simple problem that one resource. Okay. Now, if it so happens that after solving this simple problem, a next problem comes, or a slight modification is possible, which says, okay, I now have no limit on resources. No limit on resources means, if you remember that I gave an example that there is a cyber cafe, one machine is there, but nowadays computers are very cheap, so you can afford actually to as many machines as you like. So the limit, there is no limit as such on the number of resources. So that means if there are n offline intervals, then you can buy actually n machines, and you can give actually each one machine. Okay, so it is actually basically can be done in so you give some machine. Each interval you give one machine. You can do that. That is very simple assignment. But suppose the problem is not. I mean, problem is not to incur n machine, but as few machines as possible. Okay, so use as few machines as possible to serve all the n intervals. Okay, this is the next objective. So you have n intervals. See, earlier, what was the problem? Problem was a single machine, n intervals. Each is here also, each interval. Remember, each interval is of the form Si, Fi. Okay, and there are okay n such interval. So earlier there was one machine. My job was to maximize the number of accepted ones. Okay. This problem is slightly different. It says, I want to accept everyone. Okay. Then probably with one machine I cannot do. I need more machines. Okay. If there is no limit. Okay. If there is no limit, then the goal can be, okay, I can go for as much as I have n machines. So n machines means give everyone a single machine. So then the problem is trivially solved. So I can do it in O(n) time. That's fine. But now the question is, use as few machines as possible. So can I solve this problem with n-1 machines? If it is done, it can be done, then probably I save some money. I don't have to buy the nth machine. So this is the question. Use as few machines as possible to solve all the n intervals. Okay. So this may be another interesting problem, which is already solved in the book. Okay, you can see a slight variation of this problem is uh, a slight variation of this is used to solve this problem. Okay, so I'll not do it in here. I will rather ask you to go through it, and I hope it will not be very difficult for you to understand that. Okay, so there is another problem. So if I look at because we have things to cover, we have to cover greedy, then divide and conquer, then dynamic programming, backtracking, branch and bound, local search, all these things we need to do. So another interesting version I will discuss, which is like this. Um, let's say let's say that that sometimes what happens in real life when people come to a cyber cafe or somewhere else to do some job um, or use some resource, what he comes with some bit of flexibility. What is that flexibility? That okay, instead of SIFI, he comes with something called TIDI. Okay, what is called TIDI? To complete my job, I need this much amount of time. TI amount of time. I do not care much about where I start. Okay. Because I can start only after I come. Okay. Or say suppose every request has come, then it can come on has come. So every request is available offline. So it can start anytime. Okay. But only interesting thing is uh, instead of a particular start time or finish time, it says, oh, I don't care because I have already come. You can start me anytime because I have already come. But I need this much amount of time. TI is the duration. This duration of the time, I need the machine alone. And the second thing is I must finish by some TI. TI is the deadline. Okay. I must finish it within some deadline because otherwise I cannot stay here because I have some other jobs to do. Okay. So instead of SIFI, each interval comes with this thing called TI. Okay. Each interval comes with this TIGI. Okay. So in this case, what is the problem? Okay. So if such an interval comes with this, then how you will schedule. So one thing is, of course, you can do, I mean, what can be an objective function in this particular case? Okay. So one interesting thing that is possible is, of course, I mean, see, if you look at the second problem that I just mentioned, this problem, what is the goal? The goal is to uh, to okay, here one thing I must add, that unlike this earlier problem, this problem has similarity to the first problem, that is it uses one resource. Of course, how it will behave if I have multiple resources, that's a different story. But keep our attention to this one resource. So
Sir,
one
the screen is not visible.
screen is again not visible.
Yes.
Oh, maybe my hand is touching or something is. How to stop this? Now, okay, it should be okay.
Yes, sir.
Okay, so I have this. One interval, one resource, that is one computer to deal with, and I have multiple intervals. Okay, with the form of this TIDI. Okay, so if you just I'll just set the problem. So what will happen? How you will do it? One resource TIDI. So again, what is my goal? The goal can be to accept as many intervals as possible. So if I know that all have come, and I somehow can with this idea TIDI, probably I can, if I try to satisfy everybody's DI, okay, then it may so happen that I may not be able to satisfy everybody. It's like this. So suppose somebody's TI is somebody's, I just don't care the DIs. I care for the TI. So what I will try to schedule, I will try to schedule one after another. Say T1 duration, and then T2, then maybe T blah 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 up to Tn. Okay. So because I know that there is one resource, so I will use some permutation of them that satisfies all deadlines. Okay. Is it okay? Some permutation of the TIs, because I can pack them actually one after another, because one resource I can start as soon as one is gone. I can schedule them in this way. I can schedule using some other permutation. That means I can accept everyone in that case. That's the goal. But I shall try to use that permutation which satisfies all deadline, and then I am done. But it may also happen that there is no such thing, like none of these permutations, okay, actually satisfies all deadlines. It may so happen, because this is obvious, because if everybody's deadline is, I mean, very close, or the same deadline, suppose everybody's deadline is here. Suppose something like here. Everybody's deadline is here, suppose somewhere. Everybody has come at this point, and suppose everybody's deadline is here somewhere. Okay, same deadline. Then probably if I try to accept as many as possible, so if I try to satisfy, first of all, I cannot satisfy everybody's deadline because then I have to pack all the n jobs in this region. I cannot do that because I have only one machine. Okay, so I have to extend the boundary of this. So I cannot satisfy deadlines of many. And as a result, what will happen? Somebody is bound to miss deadline. Okay. Okay. If somebody is bound to miss deadline, then what is the way I can finish? So let's say I can define that, okay, if somebody starts at some time is I, that now instead of given, I have to give that to the job I, and its finish time will be given by SI plus TI, something like this, because it needs TI amount of duration. And this, I'll be happy if this FI is actually strictly less than TI, less or equal to TI. I'll be happy because then it doesn't miss the deadline. But to accommodate all of them or more and more jobs, it may so happen that I have to incur more missing deadlines. That means for many jobs, if I try to accommodate all of them, then I know that for many of them, this thing will be the case that FI is actually greater than DI. The exact finish time is actually much more than the deadline. Okay, so in this case, how do I measure that? How did my scheduling performed? Okay, how was my scheduling? So in that case, I introduce a measure. I can make many measures, but this is one way of dealing with this. I define one term called lateness. Okay, and what is the definition of lateness? That is finish time minus deadline time. So if my finish time is earlier than deadline, then I just ignore this. This lateness is essentially is negative in that case. So I just ignore this lateness. Lateness I give 0 basically. I don't consider it late. It is well and good. But in case Fi is greater than DI, this term has some value. Fi minus DI has some value, and that defines the lateness. Okay. If Fi is less than equal to Di, then it should mention it is earliness. Okay, earliness I do not consider because I'm finished early, I'm good, I'm happy. Only I care about the lateness. Okay, so how the consideration is now I should schedule all the intervals in such a way that there may be several objective functions. One is mean average lateness. Okay. So average lateness is one thing. Average lateness is these lateness values. Let's say this is equal to, I say delta I. I designate this as delta I. So I just take the average of all such delta values, and that I want to minimize. Okay. There may be other ways to do that. Also, other parameters, other things can be defined in terms of lateness. But there is one issue with this average lateness. I give an example. Let's say 5 plus 6. I consider two cases, two things. One is 5, another is 6. So what is the average? Average is 5.5. Okay. But I take another one, 10 comma 1. One job is 10 unit late, another is 1 unit late. The average is still 5.5. But which one I would like? I'd probably like this one because here each of these jobs are actually close to the average. Okay. Here, although the average is this same, but one job is finishing too early. I mean, very small amount lateness. The other job is hugely late. And somehow, because there is very small late and huge late, the average is making somewhere in the middle. But I can say that these are far away from the average. Okay? So a better terminology or better thing will be to minimize max lateness. So if I so there is max lateness. Max lateness means suppose I have this if all delta values, say delta 1, delta 2, etc., etc. Out of all these delta values, I find out the max. Okay. And that thing I want to minimize. That means in that case, that somehow some sort of guarantees that all the other people which will be late will maybe late, but they will be not more. They will be late by not more than some max value, something like that. Okay. So that's why this problem is called the minimizing the maximum lateness value. Okay. Okay. So this is another version. So what is the problem? I again just iterate. I instead of SIFI, I have all the intervals coming in the form of TIDI, where TI is job duration and DI is the deadline. Okay, you have one resource only. And what is the objective function? Objective function is to minimize the maximum lateness. Okay, you should solve this problem in such a way that you minimize the maximum lateness. Okay, so I just introduced the problem. If you go through the book, you will see that there is a detailed things. We will discuss this, but we will take this and we'll move on to other problems because a lot of problems are there. And then there are actually many other important problems to look into. So we'll see what can be done. Okay, I stop here today. If anybody has any questions. Hello? So I'll rather stop the sharing. How to do that? Okay, I think the sharing is stopped now.
Yes, sir.
Mm, what is wrong? Hemraj,
Yes, sir.
yeah, so uh, I cannot, today I could not take the that thing, how to do that, because this,
Over the participants tab,
huh?
in the participants tab.
Where?
Hello, sir.
Huh?
The option is available in the participants tab.
No, the participants tab I do not see in this meeting actually. Mm, how to look at that? Oh, meeting participants. It is showing,
Yes.
hello?
Yes, sir.
It is
Yes, sir.
showing actually meeting participant 105, meeting some 24. Others have probably left, and nothing else is showing. Actually, it's not like the other one actually.
Okay.
Anyway, I think yeah, it's not clear. Anyway, I think we can come to the group chat. Okay.
Okay, sir.
Uh, okay. If there any student, we are signing off. Okay, you can pose the questions later.